NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Proxima Centauri, the nearest star to our planetary group, has for some time been a subject of interest for stargazers. This little red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, just 4.24 light-years away, it remains invisible to the naked eye due to its relatively low brightness. However, Proxima Centauri holds immense scientific value, especially as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and significantly longer-lived than stars like our Sun. Their low glow makes them challenging to observe, but it also means their habitable zones are much closer to the star. For Proxima Centauri, this translates to an orbital distance of 0.05 astronomical units, a mere fraction of the distance between Earth and the Sun. This proximity exposes Proxima b to intense stellar activity, including frequent solar flares and elevated levels of radiation, creating an environment drastically different from Earth's. The discovery of Proxima b was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima b, marking a breakthrough in the search for potentially habitable worlds beyond our planetary group. While ground-based observations have provided valuable insights into Proxima b, they come with significant limitations. Atmospheric distortion and light pollution disrupt the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, such as its mass, distance from the star, and orbital characteristics, is based on indirect measurements. To uncover further details about Proxima b's environment and its potential for life, advanced observational instruments like the James Webb Space Telescope, JWST, are essential. Proxima Centauri's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima b, in particular, represents a tantalizing prospect. A rocky, Earth-sized planet with the potential to harbor water and possibly life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope, JWST, isn't just another tool in the field of astronomy. It is a revolution. Designed as the successor to the Hubble Space Telescope, JWST was envisioned to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the universe, its capabilities are confined to visible and ultraviolet light. JWST, in contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and reveal phenomena invisible to Hubble. One of JWST's key design features is its primary mirror, which spans an impressive 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to collect significantly more light, making it capable of observing very faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror is composed of 18 hexagonal segments that work together to create an exceptionally sensitive observational platform. Another crucial innovation is JWST's 5-layer sunshield, which keeps the telescope's instruments at a constant temperature of about -233 degrees Celsius. This ultra-cold environment is vital for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2. A stable position approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain uninterrupted observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima b. Its focus on infrared light is particularly significant, as it enables astronomers to study redshifted objects, phenomena whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its cutting-edge instruments, including the near-infrared camera, NIR-CAM, the mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIR-SPEC, JWST is not just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima b has captivated scientists and the public alike as a potential second Earth. Situated within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a key ingredient for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima b is likely a rocky planet similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our planetary system. However, Proxima b is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow habitable zone with conditions mild enough to support life. The challenges posed by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can produce bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima b retains any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain optimistic about the potential for life on Proxima b. The planet's location within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reservoirs. Life could adapt to the harsh conditions, much like extremophiles on Earth, organisms that thrive in extreme environments, such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or novel biochemical processes. Life on Proxima b is something other than a logical undertaking. It is a journey to respond to one of humankind's most established questions. Are we alone in the universe? Proxima addresses an enticing chance, a rocky, Earth-like world that could hold the conditions vital for life. As our innovation propels, so too does our capacity to investigate this charming planet and uncover its mysteries. While Proxima b presents tempting possibilities, its environment is significantly influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and significantly less luminous. Its diminished size and temperature mean that its habitable zone is much closer, pulling Proxima b into an orbit just 0.05 astronomical units from the star, about 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might harbor. One significant issue is Proxima Centauri's stellar activity, particularly its intense and frequent solar flares. These flares are sudden, powerful eruptions of energy that release high doses of X-rays and ultraviolet radiation. Such events are far more common and energetic in red dwarfs than in stars like our Sun. For Proxima b, this means a constant barrage of high-energy particles, which could strip away the planet's atmosphere over time. Without a protective magnetic field, any atmosphere on Proxima b would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima b retains some of its atmosphere, the radiation from Proxima Centauri poses serious challenges to life. Elevated levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic compounds. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b could similarly adapt. However, the level of radiation resistance required would be extreme, possibly necessitating entirely new biochemistries. Interestingly, Proxima b's tidally locked nature might offer some protection. While one hemisphere faces constant radiation from Proxima Centauri, the planet's dark side could serve as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Similarly, if Proxima b has subsurface oceans, they could provide a stable radiation-free environment where microbial life could thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima b's extreme environment provides a unique opportunity to study life's resilience. By understanding how organisms might survive or even thrive under such conditions, researchers can broaden their understanding of what makes a planet habitable. Proxima b isn't just a potential home for life. It is a natural laboratory for testing the limits of life itself. The planet's proximity to Earth and its position within its star's habitable zone make it an ideal candidate for further study. With new telescopes and instruments, scientists will continue to monitor Proxima b for signs of habitability and life. While Proxima b may not resemble Earth in every way, it offers an enticing glimpse into the possibilities of life beyond our world. Its discovery raises profound questions about the nature of habitability and the adaptability of life in the universe. As technology advances, we may one day find evidence of life on Proxima b, or, at the very least, learn more about the complex conditions required for life to arise in distant worlds. Until then, the search for life on Proxima b continues to captivate the imagination of scientists and the public alike. The exploration of Proxima Centauri and its exoplanet Proxima b is central to the growing field of astrobiology, which examines the potential for life beyond Earth. Over the years, research has highlighted several aspects of this distant system that make it a viable target for ongoing investigations. For one, red dwarf stars like Proxima Centauri are the most common type of star in the galaxy, meaning that understanding systems like Proxima Centauri could provide valuable insights into countless other star systems. Red dwarfs have lifespans typically much longer than stars like our Sun. Proxima Centauri is expected to remain active for billions of years longer, offering a stable environment for any potential planets within its habitable zone. This extended duration allows for the possibility of life evolving over long periods, potentially leading to more complex forms of life that could withstand the harsh conditions imposed by its parent star. In fact, red dwarfs like Proxima Centauri may potentially host multiple Earth-like planets in their habitable zones, opening up the fascinating possibility that such systems could harbor not one but several habitable worlds. One of the questions surrounding Proxima b is whether it has developed an atmosphere capable of protecting life. Without a magnetic field, the planet could face the erosion of any atmosphere by the intense stellar flares from its host star. However, new research suggests that if Proxima b has a thick atmosphere or an active geological history that could generate a planetary magnetic field, it might still retain an atmosphere long enough to support life. In fact, scientists have speculated that life on planets orbiting red dwarfs might be significantly more resilient to radiation than on Earth, evolving mechanisms to cope with high levels of radiation and extreme environmental conditions. The process of planetary evolution also plays a crucial role in determining whether Proxima b could be habitable. If the planet has experienced volcanic activity or plate tectonics, these processes could contribute to a stable atmosphere by recycling carbon and regulating surface temperatures. Such geodynamic activity would also be essential for replenishing the atmosphere, ensuring it remains thick enough to sustain liquid water even under the influence of solar flares. These possibilities make Proxima b an even more exciting prospect for future exploration. Despite its challenges, Proxima b is a prime candidate for the next generation of space telescopes. Instruments like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, in Chile could play key roles in analyzing the planet's atmosphere and searching for biosignatures, signs that life might exist or has existed on the planet. Spectroscopic analysis of Proxima b's atmosphere could reveal chemical markers such as oxygen, methane, or carbon dioxide, which would be potential indicators of life. JWST's ability to observe in infrared could also allow for better examination of the planet's surface temperature, weather patterns, and any seasonal variations, potentially providing clues about the planet's climate system. If Proxima b were to be confirmed as habitable, it could transform our understanding of where life might exist in the universe. The search for life beyond Earth is no longer limited to finding Earth-like planets orbiting Sun-like stars. Instead, researchers are broadening their focus to include red dwarf stars. Many of these stars, including Proxima Centauri, are older and cooler than our Sun, providing an environment where life could adapt in unique ways. Moreover, red dwarfs are abundant, with some estimates suggesting that they vastly outnumber stars like the Sun. Proxima Centauri is just one of many systems that could harbor planets in their habitable zones, further emphasizing the importance of studying red dwarf star systems. In addition to the unique challenges posed by Proxima b's environment, the discovery of such a planet has opened new avenues of exploration in the search for extraterrestrial life. Scientists are beginning to realize that life could take forms drastically different from what we expect, adapted to extreme conditions and harsh radiation. Even if Proxima b does not harbor life, its study could provide valuable insights into the broader questions of habitability and how life could survive and thrive on planets around red dwarf stars, enhancing our understanding of the universe and our place within it.